Thanks very much. It's a real pleasure to receive the Virginia Chadwick Award. And I'd like to briefly thank the Virginia Chadwick Memorial Foundation and ARC Center of Excellence. It's a great award. I really thank the center for recognizing the role that the students play in this field and in the center. And I'd also like to take the time to congratulate Jenny Dolson and Shane Blows, who also received this award in the same year for their work on the acclimation of tropical reef fish to climate change and the optimal design of marine reserves. Today I'll be talking a little bit about the work I've been involved with during the course of my PhD, and it follows very much in the footsteps. It follows very much in the footsteps of what we heard this morning with the talks from Simon, Glenn, Michael, Jeff, and hopefully I haven't forgotten anyone. But this brings us a little bit closer to our own shores, to the Great Barrier Reef, and talking about our fisheries species here, which are our main fisheries species here, which are coral trout, and another little character, the striped snapper. So the Great Barrier Reef, of course, is a very large and diverse area, and managing such a place can be a very big challenge. And today, a third of the Great Barrier Reef Marine Park is within no-take marine reserves. And this is really the greatest protection that we can afford our marine environment, but also our cultural heritage. But of course, many of us living on this coast enjoy the Great Barrier Reef for different reasons. It's a very high multiple use area. And the Great Barrier Reef supports $5 billion tourism industry, a very healthy live export of coral reef finfish. It is, of course, the pathway to Australia's mineral exports and central to the culture of traditional owners. And so we all want a piece of the Great Barrier Reef to take home with us, but we have to recognize that these activities can have an important impact on the health of this fragile ecosystem. And so marine reserves are a very effective way to minimize these impacts. But they also come at a great cost, and mainly to the fishing industry. And so the no-take marine reserves in the Great Barrier Reef have no real fisheries objectives. And so when we close a third of the reef, then it means that we also have to reduce our fish quotas by a third. And this is the case for coral trout. Yet we've known for a very long time that as we close areas of the sea, the number of fish increases and the size of fish also increases. And because these larger fish have a larger reproductive output, then in theory, these areas could have a much larger influence on the replenishment of neighboring populations. And in the long term, perhaps even support the fishery. Now, the theory has been around for a long time, and it's fairly logical. And it hasn't really been challenged yet. And I'm sure that as chair of the Great Barrier Reef Marine Park Authority, Virginia Chadwick would have been accustomed to the challenges of trying to convince recreational and commercial fishers that closing off a third of the reef would ultimately lead to better and more reliable fishery yields. But unfortunately, understanding how marine reserve works and how population dynamics work, it always comes back to this question of larval connectivity. Where do larvae go? Where do they come from? Are they going to stay home? Are they going to stay close to home where they know they're going to lead a very protected life? Or are they going to venture into neighboring areas where they're going to have to challenge the wit of fishermen? Or do they choose to migrate between marine reserves where they know they will stay protected? These questions really help us understand the turnover and replenishment of populations. And when you're managing an exploited populations, these are very basic questions that you really need to address. But there have been many challenges in trying to address these questions. And we saw a few of these examples this morning of the new technologies that have appeared in the last 15 years or so to help us track the intractable larvae. And so this all started with a pre- and postnatal tagging of fish eggs and earth-based microchemistry, and the most recent work by Simon using the carbon-13 in amino acids to track the movement of larval fish, but also includes genetic tools as well. And this morning's example on the black-tip reef shark is a fantastic example of the use of traditional genetic approaches to connectivity studies. But from many of the studies we saw this morning, parentage analysis has become more highly used in these systems because it allows us to follow larvae at a scale that is relevant to management, but it also gives us a two-way information. So we know where the larvae go, but we can also tell who produced those larvae and give us an idea of the dynamics of populations. So if we collect enough adults and enough juveniles in a population, we can measure that population's contribution to local recruitment. And we chose to put theory to practice in the Great Keppel Islands, which is an island group in the southern Great Barrier Reef. And so with great support from local fishermen and a host of international volunteers that have helped us along the way, which included me to start with, we collected close to 500 adult fish and from 3 no-take marine reserves in the Great Keppel Islands, and then went searching throughout the island group for wherever we could find these juvenile fish, and ended up with something like 500 juvenile fish from 19 different locations. And these turned out to be in proportion to the relative area that's in fished areas or in reserves. And so at the time that the study took place, we knew that reserves had twice as many, or had a twofold higher biomass of coral trout. And so we could expect them to make at least some contribution to local recruitment. And by relating juvenile fish to their parents inside reserves, we could assess the role that marine reserves have in replenishing local populations. So out of the 350 juvenile fish that we sampled in fished areas, we found 48 that we related back to their parents inside reserves. So that represents about 14% of all the juveniles that we collected in fished areas. But of course, we didn't collect all the adults in these reserves. And so, we could estimate, based on our sample of adults and our sample of assignments, how much reserves could contribute to local recruitment. And so we found that in the case of coral trout, that reserves actually contributed over 50% of all recruitment to the island group. And so this was really the first conclusive evidence that the reserves could provide a significant source of recruitment to fish populations. And that's pretty huge. Now, that wouldn't be much good if reserves were just exporting larvae to neighboring fished areas. If you could imagine a situation where you have a scorched earth outside, or where fish in fished areas never got to the age of reproduction and weren't necessarily contributing to the replenishment of populations, then who's gonna generate the recruitment in the reserves? And so luckily we also found 10 juvenile fish that we could relate back to parents in reserves. And that was either through self-recruitment or the exchange of larvae between reserves. And so interestingly, we found very similar patterns with the stripy snapper that I'll just present very briefly here. Perhaps a reserve made a lower contribution to fished areas, but a much higher contribution in reserves. And this sort of shows that maybe these connectivity patterns are variable between species, but also maybe variable in time and space. And so this was really the first study to assess the contribution of reserves to local recruitment for 2 important fisheries species on the Great Barrier Reef. And it turns out to be a real win-win for both fish and fisheries. So reserves are not only contributing to recruitment in fished areas, and therefore supporting fish population, but also ensuring that reserves maintain recruitment within their boundaries, either through self-recruitment or the exchange of juvenile fish between reserves. And as a whole, we found that the network marine reserves generated approximately half of all recruitment in the island group. And that's for both coral trout and stripy snappers. Now, that's a really big contribution to make. And how can reserves that represent only 28% of coral reef area in the island group make such a large contribution? And so we know that there's a twofold greater biomass of fish in reserves, and as it turns out, size might matter. We all know that fish, as they grow bigger, they produce more eggs, they produce more sperm, and so have a higher recruitment output. But we've never really known whether this means that that recruitment output can also translate into actually successfully putting juveniles on the reef at a local scale. So if we look at all the adults that we assign to, we find that all possible size classes contribute into local recruitment. But overall, the large majority of recruitment was assured by the bigger fish. But what's perhaps most interesting is that fish below the legal catch limit also contributed to local recruitment. And so this means that fished areas may also have a chance to contribute to recruitment. Of course, we didn't catch all the fish again. So based on the number of fish, the sample of fish that we collected and how many we assigned to, we can calculate a per capita reproductive success for each size class. And as we see here, there's a trend of bigger fish having a larger reproductive success. And of course, we know the biomass of fish or the relative biomass of fish in fished and reserve areas. And we can look at their distribution and use this information to then measure the relative contribution of reserves and fished areas. And what we see is, again, that reserves are making this almost twofold higher contribution to local recruitment. And so regardless of however we look at it, whether we look at it from the juveniles perspective or the distribution of juveniles around the reef, or if we look at the adults actually making the contribution to recruitment, then we keep finding this twofold or almost twofold difference in the contribution between reserves and fished areas. And so, although the motivation behind these closures is not necessarily fisheries management, reserves do appear to play an important role in the replenishment of fish populations. But this doesn't necessarily mean that fished areas don't generate some recruitment as well. Simply that reserves provide a recruitment bonus to local recruitment and to the island group as a whole. Whether this means that reserves can displace things like fishing effort or increase the yield of fisheries is yet to be seen, but this is very much an ongoing project that will continue over the next year, and hopefully we'll be able to look at some of these questions with some of the most recent data. Of course, PhD students and students in the center have a role, but all this work isn't possible without some of the experts and some of the leading people in this field, and I've been very fortunate to work with most of them. So I really like to give a big thanks to David Williamson and Jeff Jones, who have been incremental in this study, but all the other people, and many of you here that have been in the field with us and contributed to this work. It's been very good fun. Thank you very much.